As a coffee drinker, I usually start the day by brewing a cup for myself. This process is a fantastic example of the interplay between gravitational and surface tensive forces in a fluid. So today I'll be discussing some of the phenomena governing the movement and geometry of coffee as it drips, with an emphasis on surface tension. I will be focusing on a single droplet throughout its formation and fall before collision at the bottom of the vessel, and describe how surface tension governs what we can observe. First, the coffee accumulates at the filter's lowest point. A droplet begins to form, growing with time, and then finally detaches. There are two opposing forces here, that from surface tension, a function of the droplet's surface area, and gravity, a function of its mass. We can model this as a growing sphere. As the body grows, its volume and therefore mass increases exponentially relative to its surface area. Shown here, scaling the radius by a value will scale its surface area by the square of that value and its volume by the cube. Initially, the volume to area ratio is low, and force from the surface tension prevails, anchoring the droplet. Observe how the coffee's surface resembles a sort of elastic membrane before detachment. This is an emergent property of its surface tension. Mathematically, we can define this membrane's surface tension as the force along a length of it divided by that length. But where does this force come from? We'll get to that shortly, but for now, notice how the membrane warps just before the droplet falls. This is the gravitational force overcoming the force holding the droplet's membrane in shape. The droplet's volume and mass increase with greater order than the area, so the disparity between the opposing forces narrows, finally reaching a point where the gravitational force surpasses that of the surface tension, and the droplet detaches. Immediately after release, we can see the droplet collapse into a ball. For a second, let's ignore gravity. Now that the droplet is free of the filter in mid-air, let's discuss the physical basis of its surface tension. The coffee is composed primarily of water. As a molecule with a large dipole moment, the cohesive force between nearby molecules is relatively strong. Let's look again at that droplet from before, but this time we will model it as an ovoid, stretched by gravity the instant after detaching from the filter's bottom. Consider a water molecule in the droplet's interior. It is surrounded on all sides by other molecules. Cohesive forces pull it in all directions with equal magnitude, so it will not change position over time. Contrast this with a surface molecule. No cohesive forces exist to pull it outwards, so the net forces acting on it will pull it inwards, towards the droplet's center. The same applies to all the droplet's surface molecules, as they are all pulled radially inward, resulting in that membrane we mentioned earlier. This is the physical basis of surface tension. We can reconcile it with our mathematical definition by observing the ovoid over time. The surface molecules are pulled inwards until the cohesive force equals the force resulting from the droplet's internal pressure directed outwards. An equilibrium is reached when these forces cancel one another out and the surface area is minimized. The coffee's surface tension alone has pulled the ovoid into a sphere, and these spheres taste delicious.